All right, welcome back to part 6 of Chromosome Organization. Should be the last one. So remember where we were. We had all these radial loops attached to um, protein filaments of the nuclear matrix. This creates this radial loop domain, and we need to start connecting these radial loop domains together to form loops of it. And we got to the point where we discussed the proteins that carry that out are called condensin. There are also related proteins called cohesion, has more specific role, but works in a similar way. Both are proteins in the structural maintenance of chromosome category, which use ATP to essentially clamp around strands of DNA and the um, filamentous proteins that it's bound to. So this is what that molecule looks like. It has long arm regions and hinge region and a head region. The head region binds and hydrolyzes ATP, which facilitates it closing and clamping on it. And what happens is you get all of these strands of DNA. This can essentially clamp around anything filamentous, whether it be strands of DNA or strands of the matrix material. And the more of this there is, the tighter things are going to be bound up. So, and it's progressive. If you start binding up a little bit, the more condensin you throw in, the more it's going to tighten up. Now, cohesin is a similarly related molecule, but it has the specific function of taking the two sister chromatids and binding them together. That way, when they're lining up during prophase and metaphase, they are remaining together. And then as we start progressing through the cycle, we can start releasing those. Ultimately, there will only be some left at the centromere holding them together, and then ultimately they're released as well. And the reason why we need a separate protein for that is it needs to be turned on and off at different times. If we can't just turn off condensin at this time, or all of that DNA will just fall apart. So we need to keep that together. So we have cohesin, but it works the same way. And it just has a very specific role, and it has a different way of a different indicator for it to release. So now we've kind of gone through how we take 2 meters of DNA and wrap it inside of a nucleus, which is only 2 to 4 micrometers in diameter.